project has started in 2020 and it will end now in April 26. In my presentation, I will shortly go through and present you the consortium and objectives and activities of this Green Casting Life project. Now, the foundry sector today, it is facing numerous pressures. There are financial challenges due to the rising raw material and electricity costs, high consumption, as well as the stricter legislative and social issues. And the last two, they are related to the occupational health and environmental concerns. In this sense, the limit values are stricter year by year due to the new substance classifications, mainly VOCs, like volatile organic compounds. And VOCs mainly come from the casting process where liquid metal is poured into sand molds made of organic binder. The graph on the right illustrates the distribution of different binder systems in the foundry industry in EU. It highlights the meaning of the no-bake furan system as well as phenolic Breton cold box system and alkaline phenolic system, and all they present 90% of the chemical binders used in foundries. However, it also shows that inorganic binders are still rarely used. So the question will be, can inorganic binders be an alternative in future for reducing critical pollutants and ensuring the compliance with limit values? We received promising results already from our previous Green Foundry Life project that ended in 2020. There we had 3 ferrous foundries involved, and we made small-scale test trials. We also made several kind of emission measurements to demonstrate the emission reduction potential. And now in the ongoing Green Casting Life project, we have 6 ferrous foundries from Europe involved, and there we have carried out industrial scale tests and implementation of inorganic binders. The foundries involved, they have purchased also equipment that were needed, such as sand mixers and sand reclamation unit, in order to start the full-scale implementation by the end of the project. So the project objectives, they are as follows: to implement the inorganic binder systems in 6 ferrous foundries, including also investments and purchases of the new equipment, to design these tailor-made inorganic binder formulations and carry out and produce these implementation plans for each foundry. Main objective was also, of course, to reduce the harmful emissions from sand molds by 70 to 90%, and to demonstrate different sand reclamation methods so that we could find suitable treatment method for each partner foundry. And to assess the replication potential of inorganic binders, we made questionnaires and interviews, and among those we chose 15 follower foundries for small-scale pilot tests. And of course, as this is a live project, we have carried out wide dissemination activities, and among those we have arranged national workshops in 6 countries where we have shared our results and experiences in each these 6 flagship foundries. The consortium is big. We have in total 16 partners from 8 countries, and the flagship foundries are Peyron in Finland, Hes and Metamsa in Spain, Opsa Foundry in Poland, Valu Mehanica in Estonia, and FA Assisi in Italy. We have also universities such as AGH in Poland and Unibec from Italy. Then we also have these metallurgical R&D centers as AZTERLAN from Spain and SETIM from France. And also environmental consultant companies such as Mihanite as a coordinator and foundry team as foundry expert. And the most Critical and relevant partners also are the resin providers as Santim and Peak, which have provided all the binders for the foundries. And also we have Foundry Association AF from Spain. The budget was above 7 million and EU funding was this approximately 2 million euros. We have in total 8 work packages and main focus has been in testing and implementing inorganic binders in 6 follower foundries and piloting inorganic binders in follower foundries. And here are the milestones. First, we carried out the mapping and questionnaires. Then we carried out also different kind of emission measurements on lab scale at AGH University in Poland, pilot scale tests at AZTERLAN Experimental Foundry in Spain, and industrial scale test in OPSA Foundry in Poland. Industrial implementation started with the pre-tests in these partner foundries, and work has continued until the end of the project. We also have carried out different sand reclamation methods to find a suitable treatment method for each flagship foundry. And the resultant experiences have been used for testing inorganic binders in our follower foundries. Here is a list of equipment that our partner foundries have purchased. And what is wonderful is that in the EU LIFE funding, it can be up to 60% for the total investment cost. If the equipment it is purchased for the needs of the project and it is committed to be used for the same purpose at least 5 years after the end of the project. One of our objectives was to map the current experiences of inorganic binders in ferrous foundries and the interest in testing and using them in future. So the aim was to contact 200 ferrous foundries and email the questionnaire to them, but we contacted over 500 foundries. And the objective was also to carry out 100 interviews, and we have completed 97 interviews so far. And the Green Casting Life toolbox was made based on the questionnaires and interviews, and results were used for the selection of the follower foundries. So my last slide is just to summarize some key points from the interviews that we carried out. And among those, the advantages were like environmental improvements and waste and emission reductions, also improvements in occupational health and safety conditions to reduce gas evolution and improvements on the surface quality. And the use of inorganic binders strengthens the foundry image with the clients. However, some weaknesses arise from the limited implementation of inorganic binders in ferrous foundry industry and the potential technical problems, and required also initial investments and equipment and process adaptations. And finally, the most significant threat was the loss of competitiveness resulting from the generated costs and potential quality problems. So this was my presentation. I think we don't have yet any questions to this, and I think we will continue with the most relevant presentations now. And now we start presenting the results and experiences from the foundry participants. And first, I would welcome Martin Rockenschaub from Hess Foundry. Please, you're welcome.
Hello and good morning together. I hope you can see my screen right now. So my name is Martin Rockenschaub. I'm working in Voestalpine Railway Systems Hess, close to Bilbao in Spain. We are a foundry which produces railway crossings out of manganese steel. You may know a normal turnout for railways where the trains are allowed to switch from one track to the other. there is a turnout needed for that, and the part in the middle of the turnout where the two rails cross each other, that's called the crossing, which is usually made out of manganese steel and is casted here in our foundry. So during the Green Casting Life project, we tried to find out if we can use inorganic binders for our specific products and what we would need to adapt and what are the results. So we did, first of all, we did during the project in the beginning a lot of tests with some cores in the foundry. Later on, we also got a portable mixer where we could complete a complete mold with inorganic binders of a crossing as well. So on a first test, we molded 2 pieces from double pattern with internal description. Drag and mold were totally made with inorganic binders and olivine sand. You see for the cope and the drag, we started the test on the 7th of May last year. We used 1.8% of resin and 80% of catalyst. For cope and drag, we did add no additive. The additive, you may notice that inorganic binders without the additive, they are quite hard, that they have a quite tough collapsibility. So it's quite hard to remove all the sticky sand in the shakeout, but with the added additive, we can improve this behavior a lot. So cope and drag, there no additive was needed. We just added the additive for the cores. What we noticed, the first cope, even after bench life with 29 minutes and stripping time after around 1 hour, the first cope was breaking when turning over. So we made a second cope with a little bit more resin, which finally then was successful, the final attempt. For the cores, we did add 0.5% of additive for the better collapsibility and also 2 sets to find out which percentage of resin works best. After that, we did the casting, the cooling and the demolding. You see the pieces right here after 4 minutes in the shakeout. It's a quite short time for us in the shakeout as we have a lot of cores inside here. This is it's called an insert. It's one of the most complicated pieces we have in our product portfolio because it has many cores, many holes, quite a complicated design. But you see, even after 4 minutes in the shakeout, the sand removed quite good. After that, we placed it the second time in the shakeout and the sand was removed even better. We had to do this as we normally use only chromite sand, and in the shakeout we need to, we shall not mix these 2 types of sands. So let's come now to the results. You see on the top the cores with 1.8% resin, in the bottom the cores with 2.2% resin. Additive in both ones, 0.5. Catalyst, also 18% in both, but in the below one we used the low and the fast one, a mixture. But you see the collapsibility, it was quite good, even in the holes. We could remove all the adhering sand out of it. Maybe a little bit is remaining on the bottom, but that is something we also experience when we use our normal process with chromite sand and furanic resin. Also in the holes, the collapsibility was quite good and the surface quality was better than I would say than our chromite with furanic acid molds. However, some of our cooling blocks were shifted, but I have to say this is most likely due to manufacturing error. Our staff, it was not used to the new system, so I wouldn't take that into consideration. I would guess it's a manufacturing error. We have a comparable good surface collapsibility, and although some cores did not collapse completely in the shakeout, we have a similar behavior with chromite and furanic resin in that case as well. We also made a second test with one piece of another pattern. You will see this is quite a long piece, so depending on the design of the crossing of the turnout, the crossing can get, like in the first case I showed to you, about 1.8 to 2 meters long. In this case, it is 4.6 meters long. Also here, cope and drag were molded with the inorganic system. However, for the drag, I have to say, facing sand is olivine with the inorganic geopol system, but the baking sand is chromite with furan. This is only due to the fact it was a test mixer we had. The mold was really big. We needed a lot of sand. And during manufacturing of the mold, we ran out of sand. Nevertheless, for the cope, we fully molded it with inorganic binder. And for the test, it still was successful. Also here, we added 2% of resin. In total 18% of catalyst, no additive for cope and drag, but we used the additive to increase the collapsibility for the cores. We had only 12 minutes of bench life at an ambient temperature of 21 to 24 degrees Celsius, but it just says that we need to gain some experience with the new system. The most significant difference to normal furanic molds you can see in this picture. I took it right after pouring. So we started at the right side and then the left side was the last piece poured during that cycle. You see the black molds, the black castings. Those are the ones with chromite sand and furanic resin. And here you see our inorganic mold. And you immediately can see there were far less gases produced during pouring, far less hazardous substances. You could see it, you even could smell it a little bit in the foundry that it was different than a normal pouring. So that for me was the biggest positive impression I got during our tests. Also here for the shakeout, we must not mix our two types of sands, so we put it 2 times in the shakeout to separate it in a second basin, the olivine sand with the inorganic. But you see, even after 30 seconds, only 30 seconds in the shakeout, this picture was taken, so the collapsibility would say quite good. And after we placed it the second time on the shakeout, most of the sand was removed after we placed it a second time on the shakeout. So after heat treatment, we also need to do a heat treatment to our crossings, and afterwards they are sandblasted. So there was more or less not any adhering sand anymore on the cast piece. In the direct comparison, you can see now on top the olivine casting with olivine sand with sodium silicate, the casting, and on the bottom, in direct comparison, chromite sand and furanic resin. And when you compare the pictures to each other, you see the surface quality is for the sodium silicate far better than for chromite sand with furanic resin. Most likely due to less gas formation during pouring and those things, but that was really impressive to see. So when you take a close look, also here on that slide, on the top inorganic binder, on the bottom normal furanic resin, you see in direct comparison here at the radius, we have far less surface discontinuities. The surface overall was I would say at least 2 to 3 classes better than normal. We have significantly less gas voids, and yeah. Here the only thing, we had a lot of pinholes, which was a problem in our pattern. We shifted the ingate slightly, so these pinholes here in that area I would not take into account. So the collapsibility, to sum it up, the collapsibility, I would say with the added additive in the cores and some complicated parts of the pattern is quite comparable to the normal system. The only disadvantage we have seen was that the sand strength is significantly less. So we, in our case, we need to gain more experience to that. We have big casting pieces up to 12 meters in length, which can be a problem then if you have less sand strength. But from our point of view, the results are really promising, and we think that we can make in future our molds with inorganic sand as well. Thank you for your attention and open to questions.
Yeah, are there any questions to Martin, please? Then if not in this stage, then we can go on to the presentation from Metalúrgica, Madrileña, shortly abbreviation as METAMSA. Please.
Yes.
Sofia
Yes.
Feltra.
Yes, me in representation of David, I will make the presentation. So I'm going to share the screen. You can see the screen?
Yes.
Sorry?
Yes, we can. Yeah.
Yes? Okay, perfect. Okay, so the main objective of the project was to move towards zero pollutant emissions in iron and steel foundries in all Europe. So replacing traditional organic binders with inorganic binders, which are much cleaner. So the mission is to demonstrate that steel pots can be manufactured on an industrial scale using inorganic systems while maintaining part quality and reducing toxic gases, bad odors, and emissions to the environment. But this was not only a laboratory research, but real testing in actual foundries like ours.
Sorry, Sofia, could you please put it in full screen? Because we are watching, like, maybe it's better.
Okay, a ver.
Abajo, a la derecha. Si no, no pasa nada. Ahora estás muteada, creo.
We are going to change the computer. Wait a moment, please.
Never
Can you see the screen now better than before? I can pass the slide from one to another one.
No, I think it's the same, but don't worry, it's okay.
I'm moving the screen. I'm moving from one to another one. Can you see the different slides?
Yes.
Yeah.
Yes.
Yes, okay, so we continue.
Okay, so I was talking about our company. So I was going to explain a little more about Metalúrgica Madrileña so that you can have some context. We are a steel foundry founded in 1953, located in Alcalá de Henares in Madrid, and we have 3 production lines: 1 green sand line and 2 chemical sand or no bake molding lines, where binders were used. So we manufacture a part ranging from 5 kilograms to more or less 2,500, including both large parts and long production runs. Okay. So in foundry production, it is always necessary to find a balance between the mold strength, the easy shakeout and collapsibility, the good surface finish, and the low environmental problem. With current systems, like green sand is more environmentally friendly, but it is not suitable for all parts. The organic binder provide good quality but generate many pollution gases, and the inorganic binders are cleaner, but there are doubts about their technical performance. So our work development is that in the project, almost all stages of the production were studied, like the sand preparation, the core manufacturing, the mold manufacturing, also the steel pouring, the shakeout, the sand recovery, and the part cleaning and quality control, of course. And it was not only about changing the product, but about understanding how it affects the entire foundry process. So we did a test planning before starting because we prepared a plan about health, safety, and environmental regulations, which were reviewed. So the pre-tests were carried out in our laboratories, and the real production parts were selected. And the parameters to be measured were defined, such as the strength, the hardness, the defects, and the emissions. Okay, so now I'm going to talk about our team. About more or less 17 people from the company participated in the project, including the mold and core operators, the laboratory staff, and the production managers. But there was also an external cooperation, for example, with the metallurgical research centers, such as AZTERLAN, and other sector associations, and other material suppliers. Okay, so now I'm going to explain a little more about the test with the different suppliers and the sands. The main groups of the test were carried out with different binder suppliers, which were Sand Team, Foseco, and PIC. So, and we work with different types of sand, which were silica, chromite, olivine, and ceramic sand. And real cores and molds were manufactured, real parts were powered, and the entire process was evaluated. However, we found some problems during the tests. Like some cores broke when being removed from the core box, and in some cases the bench life of the sand was too short, and in other ones it was too long. And with some suppliers there were problems with the sand sticking to the casting surface. But overall, the important point is that all these problems are considered adjustable through the process changes, and no serious system failures. There were no system failures. So about the part quality, after the shakeout, the cleaning, and the machining, all the parts were inspected for the external surface, the internal areas, the defects, and the final quality. So what we found? Well, in almost all cases, the quality was similar to the current system. There were no serial problems, and the parts were acceptable for production. So this shows that inorganic binders, for us, they work eventually. Okay, so about the environmental control. Yes, about the environmental control, we also, it was a very important part of the project because it was measuring the real emissions during the mold manufacturing and the steel pouring. And we measured the following things like polluting gases, the dust, the organic compounds, and the values were below legal limits. And in addition, there was no visible smoke and no strong odors. So this represents a major improvement for the workers and the surrounding environment for the foundry. And then beyond the live project, Metalúrgica Madrileña decided to go further and study whether the sand could be recovered and reused. And the results were good for us. Like about 70 and 75% of the sand could be recovered. Molds were even produced with 100 reclaimed percent of the sand, sorry. The residual sand was no hazardous, and it can be sent to normal landfill or even used in brick or concrete manufacturing. And this greatly improves the sustainability of the process. So after all of these studies, we had a final conclusion. The main findings of the projects are that inorganic binders significantly reduce the pollution, they improve air quality inside the foundry, they are compatible with most parts produced here in Metalúrgica. They work with different types of sand, they allow recovery of a large part of the used sand, and they do not generate hazardous waste. And I think this is in general what we have to say. For a company, this project is also very important because it allows us to anticipate future environmental regulations, and it proves that steel can be manufactured in a cleaner way without losing quality. And that will be the end.
Thank you, Sophia, for your presentation. And since you have so many slides, I just want to repeat for all the other participants that you can see these presentations on our website, placed at AZTERLAN's website. So there you can see all the missing slides here that you didn't thoroughly see. Thank you, Sophia. Any questions to Madame? If no, then we go to our third foundry, partner foundry presentation, and it is the foundry di Assisi, and we have Ivan Stefani and Maria Pia Pascucci.
We need. Hello, good morning.
Good morning.
Good morning. We had a problem with the connections with the PC of Mr. Stefani, so we have some delays. Can we postpone with next one? Is it possible? Because Mr. Stefani is having a problem with his PC. I don't know what's happening.
Maciej,
can we postpone
yes.
to next one? Okay. Thank you. Sorry.
Maciej, are you available?
I fully agree. Okay. So just I will start with my presentation. Give me a few seconds.
So Maciej Królikowski is from Odlewnie Polskie Foundry in Poland, and he will give his presentation now. Thank you, Maciej.
Just confirming that you are seeing not this. Give me a few seconds. Okay. It should work correctly right now.
Not yet.
Okay. Now?
No. Not even yet.
Okay. So I will try to do this in the old version. So. I'm guessing that you right now you don't see also.
No.
Maciej.
I'm blocked with the sharing, so I don't know what is happening because I cannot share anything right now. I see only screen from Metamsa. Okay, do you see right now?
No. Could you email the presentation to Orois?
I would like to share the presentation because I got filmed there with the pooling session, and this is most critical and most important thing.
Wonderful.
So
okay.
give me just a few seconds. Give me 10 seconds. I will reconnect, okay?
Yeah.
If we can, PC is now available, we can step in just to support.
No, yeah, let's go. So, okay.
Okay. So we start.
You're welcome.
Okay, so we share the screen with the presentation, okay? I share my screen, huh?
Not yet.
Yes.
Eccolo qua, sono pronto. Sono pronto.
Okay. Here we are.
Wonderful. Now it seems to be okay. Your presentation is there. Please.
Can you hear us?
Yes,
Okay,
please
good.
do start. Yeah.
Thank you. Sorry, but okay. This is an introduction of the project.
Maria, you are muted now.
Yes, Maria, you are muted, I think.
Ivan, Maria, non vi sentiamo.
Yeah, Ivan, Maria, you are muted. I think we can't
Okay,
hear
now,
you.
Can you hear us now?
Yeah.
okay.
Yes.
Now?
Yes.
Yes, now, yes.
Yes.
Okay, good. Fonderie di Assisi, sorry for all these issues, but okay, as you can see, we are located in a strange place below a mountain, so a connection is not always very good. Okay, Fonderie di Assisi is located in Italy, in the center of Italy, in the town of Assisi, and what you can see here is the town, and this is where the foundry Assisi is located. So I don't know if you know a bit the history of Assisi. Assisi is a very famous town all over the world because mainly for religious reasons. And there are several important monuments, and for this reason, environment is a really important topic in our company because the surroundings are really very famous, very known all over the world, and everybody wants to maintain and safeguard this our environment. So we are really very focused to concentrate several efforts and several investments towards green production. Okay, this is a short presentation of the cast iron. Okay, our foundry produces castings in cast iron, several alloys, and stainless steel. 148, 49, 49, 148, 48, and so on. And we have worked a lot to achieve and to use a sand that we can call green sand foundry. Here there is a short presentation of the several steps of the foundries that I think we can skip, but the most important phase in our production is the production of cores, because our production is core intensive. I mean that in all our components, we produce more than 1,000. Cores are the most important part of the process, because from the quality of the cores depend at the end the quality of the component that we will sell to final customer. Our main customers are important customers and OEM. Okay, so quality is absolutely important. So green sand is the target is to use a sand that once is burned, I'm trying to simplify a process that is obviously very complex, do not release dangerous elements. Okay, this is the process of the iron casting. This is a process of the stainless steel components. In both processes, cast iron and stainless steel sand is used. Okay, this is a pictures of the components that we produce. We go from the complex turbo manifold that you can see here, and that is in stainless steel, to other components like this that are quite small, that are in cast iron, or to exhaust manifolds. So all the components that we produce are for the engines, the hot part of the engine.
Okay. So I would like also now to describe our experience about the inorganic binder. And the experience is born in April 2023. In in this slide is possible to see our study about the inorganic binder. We start to use the physical hardening by thermo curing, and the first for a test we use this kind of the system curing, the curing system. And from July the last year we started to use CO2 inside to realize the cores. And maybe in the future, we hope to start to use 3D printing. The first test was born in April 2023, and in this case we use gray iron casting, and the first test was very important for us because with that trial we started to study we started to study the system, the inorganic binder system to realize the core. In particular, in this case, we use 3 core box. It was to realize the core, the end core course. The result of that production was which show in this picture. The smaller core was about 3 kilograms. The other one, the medium, 6 kilograms. And the weight, the biggest was 13 kilograms. We started with the study on a casting production pilot plan, and to understand what happened. The result was this: only 2 casting was good, was realized correct from 24 core to starter. And first, that trial, number 1, we understand many problems. For example, 25% the core arrive broken during the travel, was broke during the transport. Inside the oven, when we after paint, more than 19% or 80% was broken because the humidity inside increased, and the result was showing this picture. In the iron casting, many cores is not the core, the coring is not enough. So the dimension was because we chose the aluminum core box was not good. And the change between the 3 core box was very long, and is not correct to understand very well the process. So the trial number 2, 3, and 4 for the trials, we choose the kind of the iron casting. We choose the nodular iron casting with small casting less than 5 kilograms and a big casting more than a little bit 13 kilograms. In this case, we study the process to realize with 1 core box. All the core of the system, inorganic binder cores, was realized with one shot. In that shot, that core box was positively studied with the thermic oil system to curing in near the shape of the core, the core. In this case, for the trials 2, 3, and 4, was in the right condition to compare the different binder. In the trials 2 and 3, we started to use Foseco and Centim. And the result was about the core the objective was about the core collapsibility, the internal cleaning after the shot blasting, and the VOC and the BTEX emission. And for that trials, the result was acceptable for internal cleaning. Very limited penetration and fines inside the wall of the iron casting, but was not emission different between the inorganic system compared to cold box. In the trial number 4, we try to realize the course by PEAC and ASK chemical binder. And in this case, the test was about the curing times, like 35 seconds, 50, and 70, and 90 seconds. And the topic was compare the quality system and the different the cleaning behavior binder depend. A result was also in this case acceptable internal duct cleaning, limited penetration and fines, and not significant emission different for light cores like the other one. Now we start to realize the first test in with CO2 to skull and in last July, and in these days we started to use for trial 6 to scale up the inorganic binder process, because like I said my colleague before, we have many core shotting inside the foundry, and for us it's very important to realize the core inside the foundry and not by supplier around Italy, because in many cases that core arrived broken. So our study now is about the CO2 system, and the trials last July was very important because the system was good, and for manifold. But the manifold, do you say, like the test number 3 for 2, 3, and 4 is weight, is light. Now we start to realize sub-basic casting is around 20 kilogram, And we maybe to produce in these days, maybe at the end of this week or at the beginning of the next week, to realize this case. And in that case, the emission we able to is compare the emission between a core box and inorganic binder with in this case, the core is about 50 kilograms. In any case, there is some problem in organic binder system because it's not possible to paint by water paint base because the water paint base need to use the oven about 150 degrees, and the result on the surface I can show in this picture. The surface broken in many parts after 30 minutes of the drying inside the foam. I just said before, if I use small kit of the core, less of, for example, 5 kilograms, also for 10 kilograms, the result is not very compared to core box, cold box, sorry, is not very particular important. For example, in this case, we find the VOC non-metal less with cold box than inorganic binder. Is not possible. For this reason, the process with inorganic binder to use inside need to change the dimension and the weight of the cores. This is the result. For us is the inorganic binder are technically viable to industrial scale. The quality casting is the system is similar to cold box for us. And by the trial 4, we saw the time cycle is similar to the cold box process. If the decuring is not enough after checkout, that core improve the cleaning after the shot blasting. And we are sure the environmental benefits are more evident with heavier cores. So I am conclude. Thank you very much.
Thank you.
If there is some question about it.
If no questions at this stage, we have in the end of this seminar, we have a good time for discussions, and there I think we will thoroughly discuss about the state of art and how you will proceed after the end of the project. What was your outcomes? Thank you, Ivan. And now we could try to go on. Thank you. We could try to go on with OPSA presentation, Maciej Królikowski. Yes, wonderful.
Yes, do you hear me and see me?
Yes, we can see you.
Okay, thank you very much. I will start for presentation. So a few words about me and about my foundry. So my name is Maciej Królikowski, and I am the director of the R&D department in Odlewnie Polskie. We call this OPSA in this project. We are the flagship foundry that is located in Poland. We are the foundry that we call that we are the service foundry. So we are producing many of different types of the castings from 0, nothing kilograms up to 500 kilograms. So this is our portfolio. We've got huge diversification of the production. Few words why we are here and what was the idea. this topic was going through all the presentation today. So the first was the foundry, then was the city, then problem occur that smell, odors, and specific of works are not, let's say, applied and allowed by the city. So the problems of the foundry that is located in the center of the city, like my previous speakers was said, that many of people are big issue with it because of the localization, because the smell of the technology, this odor, like they say, specification of the word, and of course the EU requirements that Sarah said at the beginning of this presentation. So what are our aims in this project? So firstly, because we've got 4 different lines, and one of the line is dedicated for the PEPSET technology, that this is hand molding line, and we are making the prototype small batch of the production on this line. So the idea was to check the possible to switch from this technology, so from the PEPSET technology to inorganic technology, and if this will be possible, then make the reclamation of the molding sand and reuse it in a closed cycle. So first, what we have to test that was the pre-test, like what Sarah said at the beginning. Then we just step forward, and we have to check all of the parameters of the production in the real way, so in the production scale, and what kind of issue we found. I am just speaking about my foundry. So I am speaking about the boxless, so without any frames, without any boxes, so pure mold without anything that we are putting this on the pouring zone. This is how we are pouring right now, and we was poured in the past. So we have to verify and check all of the parameters from the molding point of view, from the storaging point of view, from the pouring point of view, and the quality, because like all of the speakers says before, the quality is most important thing. So those parameters have to be achieved, have to be on the good level, and then we could say that, okay, we could try to switch or change from one technology to another, because we have to be sure that everything will be okay. So Sarah said at the beginning that in this project that it was possible to buy equipment that will be dedicated to the inorganic technology. And in our project, in our flagship foundry, we have both the molding line, 10 tons per hour mixer, and new reclamation stand dedicated to the inorganic technology. And all of the test that was made in our foundry was made on those line. So those are the pictures from the molding line. So as I said, 10 tons per hour mixer with the buffers of the 60 tons, with the rotating table, and with the line dedicated for the coating. Then we are in the end of the process that the reclamation is implemented to our facility. Those pictures are from the last week, that first inorganic molds was put it to the frame, and we are right now checking the parameters of the reclamation of the inorganic technology. So what our test was performed in this boxless line? So we have verified and we have checked the 3 different producers of the inorganic technology: Santin, Peak, and Vesuvius. Then next step was check if we have to use the coating, and what type of the coating have to be used for the molds and for the cores also. Then lifetime, bench time, stripping time, handling, and storaging, because this is crucial from our point of view. And what Martin said before, the influence of the environmental, so temperature, moisture, and this gas emission and the smell of it. And I will show the film from the pouring. This is the most important thing. Then, of course, we are not selling the molds and issue or some solution of this issue, but we are selling the castings. So the quality of the castings, so surface defects and the geometry of it. Then, if this is possible, reclamation in the closed cycle of the production to show that this sand could be reused. And right now we are trying to make the test with the 50 up to 50% of the reclamation to the new sand, 70 up to 30, and 90 of the reclamation sand up to 10 of new sand. And of course, in the end of the day, we have to check the cost of the technology. So from the beginning, those results are from the Geopol 620 that was dedicated, that was tested in the first stage of the production in our facility. And what I could say that Sand Team, Peak, and Vesuvius have a similar results in the end of the day. So after this, let's say 6 hours, 24 hours, they are similar. But what I will show in the end of the presentation and what is most important from my point of view, we are the foundry that is dedicated in Poland. We've got winter sometimes. And right now we've got minus, let's say, even sometimes from -5 up to -10 degrees inside the facility somewhere. And this is crucial from the water point of view. And this is base of the resin of the hardener is water. So this is crucial, and this is most important thing that this environmental point is critical and it have to be solved. So we are speaking that the inorganic technology could work only in the, let's say, plus temperature, and when it's environment and the air inside the foundry is warm, minimal is warm. So in our case, we was testing the amount of the binder from 2% up to 3%, even 3 with something 3 and 2 or 3.5. But we didn't see any such kind of differences in the bending strength after immediately and after 24 hours. What is important? From all of the types of the resin of the solution, so Sand Team Peak and the Fosico, the lifetime of the mold could be from minimum 5 minutes up to even 40 minutes or even more. Because in my condition, most important was that we have to strip the mold and we have to handle it after maximum 20 minutes. So that was crucial from our point of view. So this parameter have to be solved, and it is reachable in all of the technology. But sand have to be on the minimum 20 degrees Celsius and the plus. So this is most important thing. So results after casting the parts without any coatings. So pure molding sand with the inorganic technology, the quality surface and the shaking, everything is not acceptable because it's not possible to reach the good quality of the surface without any coating. This is something what was checked, verified, and what is the solution. In our condition, we've had perfect solution after using the alcohol coating, because like previous speaker said that water-based coating is, in our case, is not acceptable because we've got huge problem with it. So when we have used the alcohol coatings, quality of the surface was, I could say that almost perfect. So this is one thing that have to be added to the technology. So surface after shot blastings with the alcohol coating, like you can see on the pictures, I could confirm that it is perfect. And because this is inorganic technology, we don't have any gases. And this is most important thing in the inorganic technology, what is the best benefit. We don't have gases in the foundry, and everyone who will be present on the pouring zone, on the pouring area when the inorganic technology is casted, it is poured, will say the same words, that this is wow, it is perfect. When you confirm, like Martin confirmed the furan with the inorganic, this is two different words. So you could see something in the 3 meters when you are pouring inorganic technology, when the furan or some others technology, the gases and this dust is all over. With inorganic technology, this issue is solved. So what kind of issue we have found? Because we have line with the boxless without any frames and boxes. We are molding molds only like it is on the picture. Then after, like I said, 20 minutes, we have to handle it, rotate it, and coat the surface. So with inorganic technology that we have tested at the beginning, we have big issue with the cracking of the mold and breaking. If that was not happening on the moldings area, it was happening on the pouring zone. Then the quality of the surface, like I said at the beginning, the quality of the surface is perfect, but the material used for the pattern plates and for the molds, for the models. So wood pattern plates, wood models are acceptable, resin models are acceptable. In our case, aluminum, steel, and iron plates or models are not acceptable because they are taking too much of the warm air from the molds, from the molding sand, and from the environment. So the gradient of the temperature and the temperature drop on the surface that is touched of the molding sand is not acceptable in the winter condition. So this is the huge issue, and this is something what we could confirm, that models from the iron, steel, or aluminum are not acceptable in this technology. In our case, even when we warm up the pattern plates, the temperature drop was too fast. So handling and lifting. We have found a solution to solve this issue. Let's say that we are in the end of the project, that we have found this solution, how to fix it, how to work with this, and I will show this on the end of the presentation. Lifetime, base life, and stripping. Like I said at the beginning, the lifetime and stripping could be taken by the catalyst, by the hardener, from 6 minutes up to 1 hour even. We have tested up to 40-45 minutes, and it is working. One point, the sand have to be more than 20 degrees. When the sand is less than 20 degrees, we are speaking about the hardening and the stripping more than 1 hour. So the quality of the molds, like on the pictures, so it is good. It's okay. So we didn't have any problems with the quality of the surface of the molding. And please tell me if you see film, because those two films will be showed from the pouring zone. Do you see it?
Mm.
Yes.
Yes.
Yes, we see.
Yes.
And this is huge advantage, and this is something what is most important. You could see that we don't have any gases from the molds that we are pouring it. In normal condition, when we are pouring in the PEP set, this is we've got a huge cloud in here. You see that the liquid iron is going through the surface of the molds, and we don't have anything. And second thing, this is something what I will explain after a few slides. That from the molds, you see after pouring, molds are cracking quite immediately, quite fast. After 1 minute, 2 minutes, the molds are cracking. And from the molds, this gas that you see, this is only water steam, so water vapor. And we have checked, we have verified, so we've got only water vapor, so steam that is coming out from the molds. So this is one thing that this is most promising technology in this world. Okay, so this is the problem of the inorganic technology. Because of the strange that is not on the high level like in the other technology, what Martin shows and told us, this issue have to be solved somehow, because I show on the picture that the molds sometimes crack or was bended in the molding zone when we handle it. If there was okay, we put it to the warehouse. Then in the next day or a few days after, we have cast them, and like you see on the bottom right corner, that because the strength was not enough, the mold cracks and the liquid iron go through. So that was the huge problem of this technology at the beginning. Then I have speak with and cooperate with the sand team, and they have adopted the resin up to my condition, and the results from this resin is quite good. This issue was solved in the end of the project. What I could show on this picture, we have made the simulation of the burning zone in the inorganic technology, that it was confirmed in the pouring. So how big amount of the molding sand was burned, and how big surface or volume of this, let's say, glasses sand is all over the casting. But as I said at the beginning, when we are using the alcohol coating, we don't have any issue with the collapsibility, with the surface, with this strength of the volume mass near to the casting. So we didn't have any such kind of issue with this inorganic technology that we have checked in the OPSA. How the parts look like before shot blastings, after shot blasting, surface was clear and was perfect, like it was said, shown previously. One issue, from the geometrical point of view, we have found that when molds are breaking, the geometry is deviating. So this issue is happening. With the new resin and with the reinforcement rod that we are adding to the mold, this issue doesn't exist. So this problem was solved. So in the end of last year, we have dedicated 3 types of the parts. That was the housing mostly for the G-box that we have tested. So we have made the test with the new resin that was redesigned and was dedicated to our foundry by sand team, and all of the test result was okay. There was no any leakage, there was no any breaks on the mold, the surface was okay, the parameters of the mold was okay, and the quality of the parts was okay. We didn't have problem with the surface, with the machining, and with the quality of the parts. So I could confirm what Martin said also before, that this technology is very promising, but it have to be dedicated to the foundry, and it have to be checked and verified in precise the condition of the foundry that have to work in this foundry. Because from my experience, I could say that in the spring, in the summer, we didn't have any such kind of issue. But in the winter, there's a huge problem with producing when you don't have sand with the temperature of the 20 degrees. And those are the results from the new resin, that is 820, with the different types of the hardener SU 121. The amount of the percentage of the resin is still the same, so we are speaking about the 3%, and total 18% of the hardener, because that was the test was made in the let's say not perfect condition, because we had 6 degree on the plus in the foundry, but the sun was more than 20 degrees. The lifetime was approximately 15 minutes. After 30 minutes, we could handling and lifting the molds, and everything was okay. We see the difference after 1 hour, that the bending strength is taking faster than in previous time. So with the previous binder from some team, and the maximum was 1.7. So this is not, let's say, high level of the bending strength, but it should be enough when we are using the rod, reinforcements rod inside the molds. This is most critical, and then we don't have any such kind of issue like we had previous time. So when I go to conclusion, this technology is very sensitive for the temperature. This have to be told that on the plus temperature, everything will work correctly. When you've got boxes, you will not have any problems with the molding, with the collapsibility, with the lifetime. Everything will be okay. So this will work. But when only when the temperature of the sand is more than, let's say, minimum 20 degrees, this will be perfect. From the 15 degrees, you will have a longer lifetime. Then this should be on the first point, this emission of the gases. From this point of view, this technology is perfect. You will not have odor. You will not have any gases in the foundry. No one cannot say anything about the gases or emissions from the molds because they will be not present. So the very low content of the organic substances that was shown in the University of Science and Technology and by the AZTERLAN, that this technology is much more better than all others, and possible to make the hybrid technology. So molds that is made from the inorganic technology, and then some cores that could be made in the organic technology. Then we will have also less emission of the gases. Bigger risk of the breaking and cracking in such kind of technology that I had. So the boxless, but you could minimize it by using these reinforcement rods inside the molds. And this could totally eliminate this issue. And the higher risk of deformation shape of the casting if you don't using this reinforcement rods. So from my point of view, I could say that we will go in the next year with this technology because we want to implement in full scale in our foundry because we are seeing these benefits. We are seeing also this disadvantage of this technology and those issue, but with good cooperations with the producers of the resins and of this technology, those issues could be solved, and this technology will work in the future in the foundries. That's I'm quite sure. And if you are in the center of the city like we, this is good way to solve all the other problems. So thank you for time. If you've got any questions, I could answer.
Yes, I think thank you for your presentation. I think from the challenges and problems into successful implementation. Finally, you made really hard work during these 3.5 years and good cooperation with the binder system suppliers. I'm happy for you. Any questions to Maciej and their foundry tests? If not, then we will go on and go to the emission measurement results. That was one of our main goal and aim also to demonstrate the reduction potential to be gained by using inorganic binders. And we have Erika. Yes, please.
Yes, thank you, Sarah. Yes, I wanted to make a question to Maciej about. He said that it was so important to have a good temperature in the sand, 20 degrees Celsius, or in wintertime. What do you do in order to achieve this temperature? Because you said that you have a reclamation technology. So in the reclamation technology, you somehow heat the sand after the mechanical treatment, or which is the step that you add in this process?
What we have done, what we have made till right now, because we didn't have any reclamations then. So we are ordering the sand with the tolerances from 30 degrees up to 30 Celsius degrees on the plus, and we are adding to the buffers. When we've got winter times, we've got temperature drop on the buffer 5 degrees per day. So this is something what is we are calculating amount of the sand that is dedicated for the production. Right now, we are on the stage that the aim of the reclamation is to add the portion, the volume of the sand with the temperature 25 up to 30 degrees from the reclamation, and mix it with the new sand. So we are saying about stable temperature of the reclamated sand that will be dedicated and directly switch it to the production. So we will try to reclamate online and on time directly to the production zone.
Thank you. So if there is no any question to Mati, I'm going to share my presentation. Hopefully it will work. Okay, do you see my screen?
Yes, we do.
Okay, so
Yes.
okay, let's check. So this is in. I'm going to check if I can add a pointer. I don't remember. It doesn't matter. Okay, so my name is Erika Garitaonandia. I work in AZTERLAN. Some of you already know us. We are a technological center located in the Basque Country in the north of Spain. And in this green casting project, we make the measurements of the emissions in collaboration with AZT University, which is in Krakow, Poland. Okay, so let's get started. Here we have a table giving a quick overview of the 3 scale measurements that we have performed in the project, from laboratory scale to pilot scale test, and eventually the industrial scale test in OPSA. Okay, so key points about this laboratory test. Of course, as we move from one scale to the next, the sample size increases, and we also expand the range of a combination of binders. For example, in laboratory test, we can see that the samples were 150 grams and the iron casted 8 kilo. We measure, well, in this case, AZT measure 7 different inorganic binders, not only no-bake, but also warm box and CO2 inorganic binders. And they compare with the organic binder, specifically the PEPSET technology. Okay, this was the measurement that they have done. Okay, in pilot scale, the samples were higher. We make molds about 100 kilo, and we casted iron about approximately 60 kilo, 1:2 metal ratio sand. And here we compare not only organic binders that are here in red color, also with inorganic binders in blue color, and also the green molding sand. So all of the combinations that are currently used in the Fonderie has been measured and has been compared. Okay, and in this last industrial scale, of course, the molds were bigger, almost up to 1.5 tons in the larger molds, and up to 400 kilo was casted. This industrial scale emission test was made in OPSA. Okay. And in this presentation, I'm going to show you the results about the pilot scale test, because they compare the 3 major binders in the current situation. Okay. Okay, so to start, we made 9 molds with different combinations. Each of the mold has 100 kilo of molds and 4 kilo of core. You can see here the patterns. This is a cylindrical part, and the part weighs more or less 60 kilo. Okay, so the molds were under 2 configurations. There were 5 trials with homogeneous systems. I mean, both molds and cores were manufactured using the same binder. We can see here in red color the organic binding system. For example, phenolic urethane, furan, or alkaline phenolic. And in blue color, we see the inorganic binders we tested, both that one is a geopolymer and the other is a sodium silicate. And we also made 4 trials with heterogeneous system. I mean, there are different binders used in the mold, and in the core. These last 4 trials represent the alkaline phenolic mold with inorganic binder, or green molding sand, clay-bonded green molded sand with both organic binder, in this case phenolic urethane that they are currently using, and also green mold with inorganic cores, both geopolymer and sodium silicate. So these are the 9 different combinations that we have measured, and these are the acronyms that we are going to see in the result of the emissions. These are in this table. We represent the percentage of binder and hardener used for each of the system tested. Okay, so for organic ones, the first 3 ones, more or less the percentage is about 1.7, depending of the organic binder. And with inorganic binders, the percentage is slightly higher, 2.5. And related to green molded sand, we use 9% of bentonite, 3% of coal dust, and 4% of water. That is this is the current, the ones that they use in green molding foundries. Okay, so this is important because later on I will show you the results, and the results are given in milligrams per kilo of mixing sand. Okay, so here we can see some of the molds and cores we have made with the 9 combinations. For example, here in the first column, we see phenolic urethane not baked. This is the mold, and this is the core, and this is the casted part. The second one is the furan system, the mold and the core. The third one is the green molding sand with inorganic core, alkaline phenolic, and so on. As you can see here, the mold is placed inside a metal box that I will show you now, which is the methodology we use in order to take the emissions, to capture the emissions. Okay, I have to say that all the molds and all the cores were made with the same silica sand, new silica sand. The only different factor in these molds are the binder system that we are using. Okay, so let's go to the test design and setup of the experimental trials. We see here in the draft, here some pictures of the experimental trial. The molds was placed inside a metal box with a flap. When we we cast the melted iron inside the mold, the flap was closed, and the gases are released to a channel, to a duct, and in the end of the duct there is a fan that directs all the gases to the sample points, so we can measure properly and compare the results from one system to another system. Okay, this methodology or this setup help us to isolate the emissions and to avoid the cross-contamination that can arise in a foundry, for example. So it efficiently collects all the gases using this piping system. Okay, so here we can see some other pictures of the trials and the equipment that we use in order to measure and to make the molds. For the melting iron, we use a medium frequency induction furnace. It has 100 kilo capacity. And for molten core making, we use a pilot sand mixer for homogeneous mixing of the sand with the mixer. And we made the molds and cores by hand. Okay, so here in this pipe, this duct, in the end of the duct, we have some holes in order to make the emission samples. And we measure temperature, particular matter, crystalline silica also, the volatile organic compounds, and the polycyclic aromatic hydrocarbons also. Okay, and this more in detail, the equipment that we use for this sampling, there were sampling pumps in order to measure individual volatile organic compounds, benzene, toluene, formaldehyde, and so on, and PAH also, and particular matter. They were sent afterwards to a laboratory in order to have the measurements. We have also some online or real-time measurements equipment to test the exhaust gases, CO, oxygen, NO2, and SO2. Okay, and when it comes to the results, here we can start with the BTEX emissions. I mean the benzene, toluene, ethyl benzene, and xylene emissions. Well, this is a quantitative analysis, and the data is given in total BTEX, I mean milligram per kilo of molding sand. Okay. So this is the legend here on the right, and I write them in the same colors than in the previous slides in order to have the idea. The red ones that correspond to the organic binders, the blue ones correspond to inorganic binders, and green molding sand with organic or inorganic cores. Okay. So this is the sum of the BTEX. So in each bar, we can see the individual components like benzene in blue, ethyl benzene in orange, toluene in gray, and xylene. As you can see, benzene is predominant in all the bars, except for the furan system, that toluene is a higher concentration, and this is because we are using toluene-based hardener, and it's because of that. And we can see here that total BTEX emissions were higher for organic binders, especially for furan, followed by phenolic urethane and alkaline phenolic systems. Then the green sand, okay, here is, okay, these are them. And if we compare with the inorganic binders, we achieve reductions higher than 90%. Emission from green molding sand fell into a middle range. And if we compare with the inorganic binders, the reduction that we achieve is more or less 65 or more than 65, depending on the geopolymer or sodium silicate we compare. Okay, so let's go now to the polycyclic aromatic hydrocarbons concentration by system. Here in the bar chart, we can see the sum of all the PAH, and here in the right-hand side, you can see the individual elements that we measure in these measurements. The data is given also in milligrams per kilo of molding sand, and we see more or less similar patterns to the BTEX I mentioned it in the previous slide. We see that the organic binders in red have the higher concentration of PAH, and if we compare with the inorganic binders, the reductions are comparing to organic binders, the reduction are higher than 94%, and comparing to green molding sand, that more or less is in the middle, the reductions also are higher than 90%. Okay, and this is related to gas emissions. We measure CO, oxygen, NO2, and SO2 emissions, and we have now in this graph carbon monoxide emissions in the left here, and in the right we have oxygen concentration, and we see that for the 9 systems during the first 60 minutes of after pouring, it's recorded all the data. Just here note that due to the limitation of the test measurements, the data above 500 ppm are not recorded. Okay, but the data is given in ppm, and higher CO emissions, more than 500 ppm, are shown with achieved with green molding sand, and this is attributed to the coal that we use in the recipe for the molding sand. That is the coal, so it creates a reductive environment. So consequently, there are higher oxygen consumption. In green molds here, for example, in the oxygen, we can see the pink line, or the brown line also, or the gray line. Okay, so we can see here that the oxygen peaks are reduced, and here that the CO emissions are the higher. The organic binders related to CO are following the green sand, mainly the furan system and alkaline phenolic system, and there are less emissions, CO emission with inorganic binders. We achieve less than 3,500 ppm here. And just to mention that in the organic binders, the peaks of the CO are immediately after the pouring in the first minutes, and with the inorganic binders, these peaks, inorganic one is the one, for example, in blue here, the peaks are after 30 minutes of casting. So this is non-exothermic reactions. Okay, following with the gases, if we go to SO2 over the time, we measure here on the left the sulfur dioxide emissions in the first 60 minutes after casting. The data is given in ppm. And here on the right hand, we have the concentration of NOx over the time. Okay, and the data are given also the first 60 minutes after casting. So here we can observe the higher peaks of SO2 emissions, reaching 200 ppm are for furan system, and this is due to the hardener that they are using, is the paratolusulfonic acid. The green sand system show the next highest SO2 emissions, higher than 50 ppm. And when it comes to nitrogen oxides, the higher emissions are given for the Furan system and grain molding sand. And the inorganic binders release much less NO2, more or less 1-2 ppm. So comparing with the rest of the system, the reduction is very high. Okay, so this is the reduction rate that we can achieve with the inorganic binders. So with the conclusion can we draw that there are significant reductions in emissions using inorganic binders, as the Fonderie told you before. They say that there were no odors, no emission after the pouring. So with these measurements, we can see objectively that the reductions are very high. This improves the workplace conditions and the reduction of also some indirect costs and lower environmental footprint also. And if you want to have more info about this test made in AGH or in AZTERLAN, for each of the scales, we have made a paper that you can see in our webpage, in the green casting webpage. That is the papers are 3, and we can see related to the emissions. We can check it in the webpage that is open, free access, and here we can see some of the objectives of the project, the results, the consortium and also the contact of the person of the consortium. And these are the scientific publications. For example, the ones that they made in AGH, confidently inorganic binders, are related to the first laboratory scale emission test. And if you click them, you can see the publication written by Angelica and their colleagues in the AGH. Okay, and the same with the ones that we made in pilot testing. Here, assessment of harmful emission from multiple binder system pilot scale sand casting. You can have more information about the methodology and the results obtained for the presentation that I have made actually, and also the one related and made in OPSA by AGH and this green industrial scale casting production using engineered molding material. You can also download this paper here. And okay, and to finish, okay, and also I write it down here, the email about in the AGH University and AZTERLAN, that you can contact us if you need further information about this emission test.
Thank you, Erika, about your presentation. We have at least one question, Stefano Saetta.
I am Stefano Saetta from University of Perugia. I would like to thank Erika for the presentation, for all the job they did in the testing, the laboratory setup, and also Angelica and Erika, both you did. I think, as you may see, the reduction of emissions was impressive using organic binder, more than 90%. So this is very comfortable that you test on the field. Also, if I remember correctly, you see the reduction of smoke. So it's also a visual impact that you may have. And I just want to say that even if in a technology like green sand, where the reduction of VOC cannot be very big in absolute value because they don't have too many organic materials, the effect, for instance, in the core shop machine where they use now organic material is much better for workplace safety and for the reduction of odors, even if maybe in some technology the absolute reduction is less effective, even if in this case the use of inorganic binder can be useful for the core shop or reducing workplace hazard, I would say. So thank you very much. This is what just would like to say, Erika and Angelica.
Thank you. Any further questions? Okay, then we can go on with the final two presentations. And now we have a presentation from SAN team, and SAN team carried out a lot of thorough reclamation tests with inorganic binders. So welcome, Michal Vykoukal from SAN team.
Good morning. Thank you, Sarah. I would like to try to share the screen. Do you see my screen just now?
Yes, we can.
Okay. My name is Michal Vykoukal. I'm working in SAN team, and SAN team is a binder supplier in this project, and as well we are focused on reclamation used SAN from pilot foundries. And I prepared results of reclamation on these used sand. We can reclaim sand by two ways: primary reclamation or secondary reclamation. Most common used technology or reclamation is primary reclamation, but there is possible to use bag for production, mold and core production only about 70%. The layout of this primary reclamation is generally external shakeout deck, crusher, and cooler classifier. Of course, it's possible to use secondary attrition, for example, commercial USR from Omega, and there is possible to use up to 90, maybe 100% reclaimed sand bag for mold and core production. The schema of the secondary reclamation you can see on the right side is shakeout deck or crusher. After that, dryer, cool classifier, storage for primary reclaimed sand. After that, secondary attrition with dust extraction and silo for secondary reclaimed sand. If we process the sand by secondary attrition, we can reach and achieve good results of secondary reclaimed sand. I mentioned here in this slide the main parameters, which are average grain size, part below 0.09 millimeters, maximum value 0.4%. Washable substances, maximum values 1.25%. Moisture, let's say maximum 0.25. It will be possible, maybe higher, but we will be very careful with moisture because there is a problem with handling and blocking in transport lines. Most important is soda content. We recommend maximum value 300, and conductivity we recommend 500 microsiemens per centimeter. These values are values according to our experiences with reclamation in foundries where they have secondary or primary reclamation. On this slide, you can see flexural strength for secondary sand mixture with previous mentioned parameters, with good parameters of reclaimed sand. Final strength could be 1.4 to 1.8 megapascals, and these are enough for good molten cores. Bench life usually 5 to 10 minutes and stripping time 15 to 30 minutes. Bench life and stripping time depending on used hardener. Before the reclamation with used sandfront pilot foundries, we made 3 tests in Omega with 3 different used or reclaimed sand from 3 Czech foundries. First was Iron Foundry. It's foundry using only new sand without reclamation. Sand was for first cycle. The most important parameters is soda content. You can see big reduction after first and second pass. It is promising for a high percentage of reclaimed sand for the sand mixture. Washable substances, there is a reduction, but not so. There is no difference between sand as received or after passes. But important are tests on sand mixtures. You can see strength after 1, 2, 4, and 24 hours in megapascals. The most important is strength after 24 hours. We add to the sand 80 up to 100% of this secondary reclaimed sand, and you can see we have final strength above the 1.4 megapascals. It means that it's possible to use even 100% secondary reclaimed sand for mold and core production. Second example is reclaimed sand from aluminum foundry. Aluminum foundry we choose from the reason that the aluminum is casted from low temperature, about 700 degrees Celsius, and this means the worst scenario for the reclamation, because there is low thermal load of the sand. Again, soda content, good reduction of washable substances. We add 50% secondary reclaimed sand and 100% reclaimed sand, and the first series is 0% of secondary reclaimed sand. It means the sand was made in 100% new sand. It's for reference, and you can see the final strength are almost the same on the level of 1.4 megapascals, and these parameters are almost the same with the sand and properties in the foundry. So it's possible to use 100% secondary reclaimed sand. And the third sample is from Iron Foundry. It's reclaimed sand. The foundry has only primary reclamation. It's necessary to say that the primary reclamation is pure quality, but we can see that there is small reduction in soda content, and washable substances are almost the same. There is a very small improvement. It's in reclaimed sand quality. And on the graph with structural strength, we can see that it's possible maximum to add 50% secondary reclaimed sand to achieve strength about 1.7, 1.8 megapascals. More reclaimed sand than 50% has a very low strength, and it's not possible to use. For this reclaimed sand, it's necessary to say that we work with primary reclaimed sand, and after several cycles in secondary attrition, the parameters will be improved, and the percentage of secondary reclaimed sand to the sand mixture could be increased, maybe 75% secondary reclaimed sand. So it was examples from USR secondary reclamation. And just now I would like to show you results on 8 samples which we had from 5 pilot foundries under the project. We had one sample from foundry Metamsa. It was with binder system Fosico, and only this sample was used sand or reclaimed sand from their existing reclamation and from their existing production. It means the reclaimed sand were after several cycles. The rest of samples was made from new sand. It was first cycle. It means one molding, one casting, one reclamation. We had 3 samples from foundry Peyron, from binder system Geopol, Peak, and Fosico. 1 used sand from foundry Valumechanica with Geopol binder system. 2 samples from foundry OPSA, binder system Peak and Geopol, and 1 used sand from the foundry Hess, and it was in a Geopol binder system. Last 6th foundry is foundry Assisi. As Ivan described, they use inorganic binder system for core production, mainly for core production. So we focus for evaluation of the effect of inorganic binder system on green sand mixtures. These results I will not present in this presentation. Here is overview work and test made in a sand team. We made reclamation, sand mixes, and of course, we focused on waste sand classification. Work done in this project: primary reclamation, secondary reclamation. We had to done new sand and used sand parameters, primary and secondary sand parameters, sand mixtures with primary reclaimed sand and secondary reclaimed sand, and we had samples for waste classification. It was only from used sand, 8 samples for waste sand classification. And we choose 2 parameters, and we take samples, took samples from primary and secondary reclaimed sand, and sand for sand waste classification as well. From point of view reclaimed sand parameters, both for primary and secondary, we focused mainly for these parameters. Main was soda content, washable substances, electrical conductivity, parts below 0.09 millimeters, and moisture. And we measure another additional parameters like average grain size, AFS, want water, LOI, pH, and acid demand value. These parameters were measured in Santim laboratory. And in Santim laboratory, we focused on sand mixtures. We measured flexural strength after 1, 2, 4, and 24 hours. And we measure bench life and stripping time. The third part was the used sand waste classification. We focus only for used sand samples as received from the pilot foundries. The samples were sent to the external accredited laboratory, and the samples and tests were evaluated according to the Czech legislation. The analysis was focused to using used sand for backfilling, for disposal of waste at landfill, other waste, an option disposal of waste at landfill, hazardous waste, and of course it was necessary to make assessment of hazardous properties of the waste, mainly parameters or properties HP 14 and 15. For primary and secondary reclaimed sand, we focused on dissolved organic carbon, DOC, and TDS, dissolved solids. These two parameters are, according our experiences, most important for waste classification. Now I would like to show you how we process the reclaimed sand and secondary reclaimed sand. We have in Santim primary reclamation vibratory time. It's bowl crushing vessel. It's for crushing of used sand on grain size. After that, we dry the sand in a chamber drying oven. The reason were to set the same condition for all used sand. And we had two samples from Peyron. It was samples of Geopol and Peak. And both samples were delivered with high moisture content at the level of 5%. It was the most important parameter why we have to dry the sand.
Michal, just few minutes time, please.
Sorry?
Few minutes time anymore. Yeah.
Okay. After that, reclamation with dust extraction, secondary reclamation, laboratory or test reclamation installed in Santim, batch type 50 kilos with dust extraction. And I would like to show you results. This is table of results with parameters of reclaimed sand. We measured 11 parameters and had more than 50 samples. We had new sand, used sand as received, used sand after drying, primary and secondary reclaimed sand. From point of view parameters, electrical conductivity, this is parameters for all foundries and binder systems. There is good reduction in for secondary reclaimed sand. And the same parameters for soda content, very good values for reclaimed sand is the gray columns. And these parameters show and are promising for a high percentage of secondary reclaimed sand for mold and core production. Same results for washable substances. Table below the graph is efficiency for primary reclaimed sand and secondary reclaimed sand. For primary, the efficiency is between 20 to 40% in average classification. For secondary attrition, about 70%. This is full table for sand mixtures. We had more than 60 sand mixtures. Addition level was set according to the binder addition level which we had from the foundries. And the most important parameters is strength after 24 hours. You can see graphs for foundries and binder systems. For Mentamsa, it's possible to use 75% primary reclaimed sand and 85 secondary reclaimed sand with high strength 2.2 megapascals. There is promising to use more than 85%. Voestalpine with Geopol binder system. There is possible to use maximum 85% primary reclaimed sand and even 100% secondary reclaimed sand with a good strength 1.7 megapascals. Next foundry is OPSA with a binder system Peak. It's possible to use 85% primary reclaimed sand with the strength almost 1.6 megapascals. And very good results with secondary reclaimed sand. It's possible to use up to 100% secondary reclaimed sand with very good strength 2.1 megapascals. Very similar results are with Geopol binder system with OPSA used sand or reclaimed sand. It's possible to use even 100% primary reclaimed sand for mold and core production with the final strength 1.6 megapascals and even 100% secondary reclaimed sand with strength up to 1.9 megapascals. Last three foundries from Peyron, Geopol and Peak looks very similar. The sand was probably washed out before we received to something for testing. The sand have very good parameters, Peyron Geopol and Peyron Peak, and it's possible to use 100% primary and 100% reclaimed sand with very good final strength. Different is sand, Peyron and Fossico binder system. There is possible use only 50% of primary reclaimed sand and 85% secondary reclaimed sand with the strength up to 2%. Last is Valumechanica with Geopol binder system. Good strength for primary reclaimed sand. It's possible to use 100% reclaimed sand. And it's possible to use 100% secondary reclaimed sand with strength at the level about 2 megapascals. And the last results is waste classification. This is table of results. Next table is reduced and it's comments to the results. We had 8 samples of used sand. Good thing is that according to the assessment of hazardous properties, there is no hazardous property HP 14 and 15. From this point of view, all materials which we had haven't hazardous properties. From point of view backfilling, there are strictest limits for the waste sand. Almost all used sand is not possible to use for backfilling. Only 2 sand from Peyron, Geopol, and Peak. The parameters are good, and these allow to use for backfilling. From point of view disposal at landfill, other waste, all materials according to the measured parameters is possible to use for this type of landfill. From point of view landfill dangerous waste, only used sand from foundry has with Geopol binder is not possible to use for this landfill. This is the most important parameters, dots and solid dissolved materials. There is big reduction after the secondary reclamation. After the primary reclamation, parameters are below the red limit values, and reclaim sand, primary reclaimed sand is not possible to use for backfilling. The classification is almost the same like used sand. For secondary reclaimed sand is a better situation. Only material or used sand from Metamsa is for Fossico binder system is not possible to. There is no significant improvement, and the classification is the same. But all the other materials, there is an improvement, and all materials after a secondary reclamation is possible to use for backfilling.
Thank you, Michal. And I have to interrupt since we have still one presentation left. So I think you can give your email addresses, and then we have all the presentations in the OneDrive, not OneDrive, but the website. So you can feel free to ask then further questions and information from Michal. Thank you.
This is the last slide, and there is only summary of percentage of reclaimed sand and stench. So I think the results are very promising, and it's possible to use 100% primary, secondary reclaimed sand, and in some cases 100% primary reclaimed sand. But it's necessary to set that the used sand was with new sand after 1 cycle, and it's necessary to use the sand with minimum 10 cycles, and after that make another testing. Thank you.
Thank you, Michal. And to go on further, I think because we are late with our presentations, we should go to our final presentation. That is the new BREF and that conclusions that was released in December 24. So I welcome you, Erika Aries from IPPC Bureau.
Yes, good morning to everybody. Can you hear me and see me?
Yes.
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 Yes. Okay. And can you see the slides as well? Or?
Yeah.
As well.
Yeah. Okay. Okay. So thank you for inviting us, in fact, to this meeting. It's interesting to see all the developments which are happening on the front of those alternative binders. In fact, especially in this project, because it was a big topic when we revised the Smitheries and Foundry BREF. So yeah, today I was asked to give a kind of overview of the BREF. I'm not going to go into too much detail. So I'm Eric Aries, and George also was attending the meeting today. So we were both BREF authors. We work in the Joint Research Centre in Seville. And we were indeed working on the revision of this Smitheries and Fonderie BREF. So, as I say, I will not go too much into the technical details today, but just give you an overview of the new BREF. So, what is the scope? A bit about the process. How did you manage to get to this final product? The main changes that were included in this BREF, and focus a bit more on the bad conclusion, which are, of course, the most important chapter of the BREF. Okay, so just starting with the scope. So in terms of the scope, as you know, we have several activities for the Industrial Emission Directive, which are covered. So we have first the activity 2.3, so that is processing of ferrous metals, especially the Smitheries, in fact, which were actually not included in the previous BREF. Then we have 2.4, which are the ferrous metal foundries. So that covers, of course, all the foundries, including cupola furnaces, for example, with large production capacity. Then we had 2.5, which were the non-ferrous metal foundries. That includes foundries operating for lead and cadmium with 4 tons per day, and other foundries with other metals, 20 tons per day. So that includes aluminium, zinc, and this type of foundry. And then, of course, we have, that is something that we have in all bad conclusion. It's about the operation of wastewater treatment plants, which provided that, in fact, the main contribution, above 50% in general of the wastewater flow, is coming from a foundry. So that is, in fact, the thing. Okay, what type of other activities which may not be, I mean, we had quite a lot of discussion there at the start of the BREF about things which were not so clear in the previous BREF. And it was decided here to specifically include, for example, the production of gray or nodular iron castings in ferrous metal foundries, because that was not necessarily clear from the activity in the IED. Same for non-ferrous metal foundries. We had to specify. There was big discussion because people, there was an interface, of course, with the non-ferrous metal BREF. And so just to classify the foundries which are linked to the non-ferrous metal BREF and the foundries which are linked to the Smithery BREF and Fonderie BREF, we had to go through this formulation of the near to their final shape. So it was important that the foundries under this BREF produce specific final products and not semi-finished products. So that was a key element. Coating of molds and cores, so that was included, the storage, transfer, and handling, and also combustion processes were included as long as it was direct heating. So it has to be direct heating. What the BREF did not cover, so continuous casting, of course, for iron and steel. The point I was mentioning before, this production of semi-finished non-ferrous metal products. So that was a distinction with non-ferrous metal BREF. Cadmium, titanium, precious metal, forging presses. And that was interesting because there was a big push when we started the BREF to include forging presses. Forging presses were not actually, there was a gap in the Industrial Emission Directive, the previous one. They were not mentioned, in fact, in the Industrial Emission Directive. And it has been now, in the revised version, included. So we can expect probably in the next revision of this BREF that forging presses will probably be included in the next revision, probably in 8 years from now, but or 6 years maybe. But those forging presses will be looked at in the next version probably. Okay, rolling mills, that is in the ferrous metal processing BREF. Okay, so in terms of the process, well, we started early in 2018. We had a kickoff meeting here. It was in 2019. And then we elaborated a questionnaire. So there was a very detailed questionnaire that was sent to a number of plants. And we had a very extensive data collection. I mean, the data collection lasted, as you can see, more than than 1 year. So that was quite extensive. We did some data assessment workshop. We published the first draft of the BREF in February 2022. And on this draft, we received more than 1,500 comments that we had to deal with. We revised, in particular, the bad conclusion. I mean, 80% of the comments, of course, were on the bad conclusions. So we had to revise that in particular. And we prepared a background paper. We communicated again to the technical working group the revised version of the bad conclusion. And we went to the final meeting. So the final meeting took place in June 2023. And then following final steps, we managed to publish the BREF and the bad conclusion in November 2024. So that's about, a year from now, 2 years from now. Interestingly, we had a number of plants. We had a lot of plants. For foundries, we had more than 158 foundries which participated in the data collection. So we really covered, I mean, compared to the previous BREF, I mean, that was really a huge advancement, of course. So we covered all type of foundries, high pressure die casting foundries, aluminium, ferrous, cupola furnaces, induction furnaces. I mean, we covered almost everything. The lost foam cast foundries as well were included. And we, in Smitheries, less relevant for you, but we had also 9 plants. There was not many plants above the threshold. So the threshold was the IED. So we only had a few plants included in this BREF. We carried out a lot of site visits as well. So we started actually in Spain. Spain, we were invited actually before the technical working group started. We were invited there in 3 foundries, as you can see, steel, high pressure die casting, and ferrous foundries. Then we moved to Sweden. We also saw a number of different foundries here. We went to visit the largest foundry in Europe, the Stellantis plant. In fact, in Villers-Semeuse here, where there we saw the lost foam casting process in particular. And then in Belgium, the Profero foundry, cast iron foundry we visited. Okay, so what changed compared to the previous BREF? Well, first of all, very important is we added the Smitheries. We, of course, did a general update. We restructured the documents. Very importantly, compared to the previous BREF, I mean, what is important is that we really plotted all the graph, all the tables, the graphs, the data from the data collection. You can find in the BREF very detailed graph about emission measurements, also for energy consumption, water consumption, and I mean, so you can, of course, for emissions, you can link that to specific plants. For energy consumption, the data were confidential, so it was not possible to, you can see the data, but you cannot associate it with plants, but that is the way it is done. And that led us to do the bad conclusion. We had 52 bad conclusion in total, 10 which are general bad conclusion, and 35 bad conclusion specific for foundries in particular. Okay, so let's focus now on the bad conclusion. So that is the structure. We have the scope, some definitions. I mean, most bad conclusions are built like that now. So we first of all have what we call the general bad conclusions. Those are applicable to both the Smitheries and foundries. We put here the environmental management systems, monitoring, some general techniques on energy efficiency, noise and vibrations, and management of residues. So those are, let's say, more general. Then we went deeper into the foundries in particular. General bad conclusion for foundries, the bad conclusion for cast iron foundries, and steel and non-ferrous metal. So that was really the main bulk of bad conclusion, and also for Smitheries. So here it is, key features of the bad conclusion. So, well, as I said, in a general bad conclusion, we have the environmental management system here. We also included a chemical management system. So that was new. Requirements to do inventory of inputs and outputs in the plants, techniques for emissions to soil and groundwater, and other than hot knock also operations. So we have general technique on energy efficiency, noise and vibration management plants, and residue management plants. So that is also new features. Then we add specific bad conclusion about hazardous substances. So that is linked to what you have been presenting today, to limit substance of very high concern, essentially linked to the use of binders, phenolic binders, other binders that is a clear. One of the key advancements, I think, in this bad conclusion is there was a clear push to look for alternative binders. I mean, this is clear. That was the objective, really, to try to kickstart the transition of this sector, because the sector, there was a lot of, how can I say, alternative binders which were becoming available, and there was very little uptake in the sector. And I think those bad conclusions have really triggered that. So that was a big advancement. Another advancement was BATA EPL, so that's environmental performance level for energy efficiency, for material efficiency as well. And we saw in the previous presentation about sand reuse, so that is quite important. Yes, after, in terms of foundries, of course, we set up a number of emissions to where BATA EL, so that they became, first of all, more compounds were included. For example, for molding using gloss molds and core making, which is a big part of the foundries. So there was BATA EL now for dust, but also for amines, benzene, formaldehyde, phenol, and TVOC. So quite a wide range of compounds were included. The same for casting, cooling, and shakeouts. The loss from casting, that was not necessarily well covered in the previous BREF, so we got BATA EL in there for dust and TVOCs, and foundries for permanent molds as well. So for dust, lead, and TVOC. Finishing processes, we have BATA EL for water consumption, and general emissions to water as well. So a number of compounds were included for emissions to water from foundries. Those emissions to water are mostly linked to high pressure die casting foundry. In fact, a lot of them. Some other foundries, the cupola furnaces also, but I think most of the BATA EL, are linked to high pressure die casting in general for emissions to water. Okay, then we had some very specific, we put specifically, bad conclusion for which were linked to the thermal processes. That was a bit separate. So, for example, we had a bad conclusion for cast iron foundries, all the thermal processes. So here we have a very large table, if I recall, with BATA EL for dust, of course, HCl, HF, all the pollutants which are included, and related to the different type of furnaces also, because I think there was the cupola furnaces in there, the rotary furnaces, induction furnaces as well, and the BATA EL varied depending on the type of furnaces, in fact, which were used for all those parameters. The nodularization process also, there was a BATA EL set for dust in cast iron foundries. For steel foundries, so that is about mostly electric arc furnaces, I believe, maybe induction as well. There was some BATA EL set for dust and PCTDF, dioxins, and for steel refining. So steel refining, that's the argon oxygen decarbonization or VOD treatment. So there was a BATA EL for dust also set there. That was new. There was nothing, I think, before. For non-ferrous metal, there was BATA EL again for the thermal processes. So here it was, I think, linked to reverbatory furnaces, for example, or crucible furnaces in particular. And yes, and bad conclusion for Smitheries. Bon, that is probably less relevant for you, but yeah. So that is, I think that's all I wanted to say. It was, as I said, I was not going to go into very technical details today, but just give an overview of what was done. And yes, I'm happy to answer some questions if you have. So thank you very much.
Thank you, Eric. Does the audience or any participants have some questions to Erika? Yes. Okay. If not, then we could go to the discussion and closing part. And there, Ivan, Stefani, you have a question. Am I right?
I would like to introduce my boss of Foundry, Mr. Pietro Tacconi, and he have a question for maybe Mr. Aries.
Good morning to everybody. I am Pietro Tacconi, and I want to know, I have a question for Mr.
Aries. Aries, for the BREF.
For the BREF, regarding the BREF. Also, like a member of ASOFOND, our Italian association, we had several internal discussion in the association, not only in the foundry, in our foundry, regarding the application of this new rule, the BREF, for the European foundries. And also take in consideration the big political activity that is making the president of our European community, Ms. von der Leyen, regarding to expand the collaboration, the commercial collaboration with countries like India that are full of foundry and with a lot of big capacity. I was in India for several times to visit many foundries, absolutely far from the respect of the most important rule and law that we in Europe we want to apply. So my question is the application of so strong regulation in the foundry that will impose to the remaining foundry that are still in life, very few foundry compare the number of foundry that we had, I don't know, 20 years ago, 10 years ago, and that continue to go in bankrupt or they are suffering the financial situation, the automotive crisis that impose also to decrease the volume. And it's really a dramatic scenario for the European foundry. How we think that the application of this very strong rule will help us to remain in life with this very rigid and let me say ideological approach that consider Europe that stay completely out of the world. The rest of the world in Africa, in India, in Indonesia, in I don't know, in South America, and continue to work and to produce goods respecting a totally different rule. I don't want to say that they don't have rule. Maybe they have rule, but this rule is very, very different from our rule. So, which is the expectation, like a technical people, the impact of this rule in a sector that is living a dramatic situation still now.
Yeah, thank you for your comment. I mean, well, it's fair to say that you know, when we wrote and when we concluded this bad conclusion, I think the economic situation in which we are now is probably not the same, and the geopolitical context is also not the same. So, I mean, obviously, we have worked under the mandate which has been given to us under the IED. As decisions were taken by a technical working group at the end. There has been advancement, it's true, in terms of emission limits, because this is, I mean, clearly in this sector there was evidence that there was technology available to reduce emissions. I mean, I think nobody can contest that. And there was very little uptake. That was clear as well. So, I mean, the idea of implementing novel technology which are available to improve the environment, which is the objective of the IED, I think is not a bad idea. So this is what we try to do. Now, it's fair to say that the geopolitical context and the economic situation has changed. Is true, you are right. And that may affect the foundries. Us, at the European Bureau, we are not involved in that. We cannot do anything. And there is a 4 years implementation period for the SPAT conclusion. So theoretically, the foundries will need to transition within 4 years towards the SPAT conclusion and implement changes. And of course, that will cost them money. Everybody is aware of that. But I think in the Commission now, I think there is also, I mean, people are listening. You know, they know that the industry is going through a very difficult period. I mean, me, I worked a lot in the steel industry in the past, and you know, I've been involved. I mean, you've seen that with the steel industry, there has been a lot of measures which have been taken. I think it's important that the Foundries Association, maybe if there are strong implementation issues and maybe you know too much risk of plants going down, then needs to be come forward and explain the situation. I mean, that's all I can say. I mean, you see, it's but yeah, I understand.
Sorry, I understand. I agree with you, and maybe it's not the right table to put my question, but anyway, I think that it's important in this prestigious table of technicians and people that take care about foundry technologies and also make one reflection regarding all these things are very, very good. Everybody are worried regarding the emission, regarding in general the situation of pollution in Europe and not only in Europe, in the world. But for me, it's also a good opportunity to open one reflection regarding the possibility that the application of this rule has to be combined with the possibility for our industries in Europe to remain in life finally, and also the application of this rule has to be pragmatic, let me say, and gradually. I think it's not important if we need 5 years more, 10 years more to arrive to the best. The more important is to arrive to maintain our industry in Europe, our workers, the people that live of their salary, and to maintain also our technology, because otherwise all this kind of business step by step will be moved from Europe and will disappear in Europe, because the cost is one important driver. When we go to our customer to try to sell our part, price is still the most important argument to try to convince our customer. So for me, it's an opportunity to maybe it's not a possible an answer, no, in this situation, but it's important that every people, every one of us think how is important that in Europe remain industry, people, demand, companies, technology, know-how, and consider in general many point of view. Environmental is one important point of view, but also the cost sustainability. It's very important, and like technicians, we have to work also take in consideration this argument. That's
Can
all.
we also, sorry to interrupt, but there is
Yeah.
also one comment from the audience. I think he has similar kind of a topic or issues as well, but I would like to give him the floor as well for the question. Sorry to interrupt.
Okay.
Okay. Thank you. Thank you.
Thank
Thank
you.
you.
So Jan Solve Öberg.
Yeah, it's more or less the same topic, but if we are supposed to be self-sufficient in Europe on this product also, the EU cannot then make this kind of agreement that will make the challenge of being producers in Europe where they have no requirements of this kind of environmental issues on their foundries in India and other places. Then you will not have in the future foundries there, and we will not be self-sufficient on these kind of products in Europe. So when we make these kind of deals after we have got these requirements, then you need to take that into your also agreements with the in India and the others, so that we are playing on the same playground and have the same regulations. Otherwise, this will not be a positive solution for Europe.
Thank you for the questions. And now in the end, I would like to give a floor just to make an overview of the conclusions, if this is okay for you, for Pekka Kemppainen. He will present shortly about the main steps that we had.
All right, everybody. I think that it was very good, this last discussion about our project as well. So my background is that I have been 48 years in the foundry business in different positions as a engineer. I'm metallurgist. I've been engineer, production manager, foundry owner, but worked also globally in Mianat worldwide organization, which I own at the moment. And in this project, I am some sort of a consultant who would look the situation, what kind of installation possibilities we have to take this important improvement in foundry environment, internal and outside environment. So I have collected a couple of conclusions if you take the next page. So we have heard very good representations today, and it's clear that we have very positive environment impact from these inorganic binders, better surface quality, better casting. Also the one point which is better feeding properties in the castings, especially ductile iron, gray iron, because we don't have gases, but also surface finish is good, and all these harmful things will go smaller and so. And it looks that the prices for these binders is not. It doesn't differ too much from organic binders, and it became clear that most these no-bake systems like Webset, AlphaSet, and Furan can be very promising to replace organic binders by inorganic binders. But then there are some technical challenges which came up in these presentations. The mold is not so strong and so on. But the biggest problem is actually, I see it to reduce the amount of organic binders in foundry industry is how can we solve this concerning green sand foundries, because I believe that in tonnage most of organic binders are used in green sand foundries in the cores and so on. But as we saw, it's not so big influence because the cores are only a small part of the emissions in green sand foundry. But however, that is one of the challenging points. But maybe we can reclaim, if we can reclaim sand by complete burning and dedusting and or washing the sand, such wet reclamation system, that's also possible to solve. The next please. Okay, then I have a couple of things which didn't come here. So of course we could save also material efficiency was mentioned in one of those but and so on, so that we should be able to recycle our sand in foundry more and more times, not so that we get 30% of surplus sand because we have to make all the cores from new sand. So we have to get this reclaiming higher and higher level, and it was good, those primary and secondary reclamation, then we can go up to 95% and so on. But then, of course, if we start to use wet reclamation, maybe we can get it up to 100%. And one idea which I want to point out is that if we start to use these stronger, better, not so easily breaking into pieces, such sands like olivine sand or ceramic sand, which last much more cycles in thermal mechanical reclamation, less dust and so on. It's an investment, but maybe it pays back in the future. That's one point. And then one very important thing in these inorganic binders is what was done in Hess foundry is that by replacing silica sand by olivine sand to get rid of silicosis, which is again such a big advantage. Also, okay, ceramic sand is giving even better principles and so on. So these are the points, but then the next page we have the big challenges, and I just can continue the comments which came from Italian colleagues, is that who is going to pay this improvement in environmental things? And when if foundries take the step towards zero emission situation, and what the marvelous results we heard, are the customers willing to pay because we improve their product more green into their products, less carbon influence? Are they willing to pay, or do they say that, sorry guys, I get these cheaper from India, who I really agree that they don't follow the rules. And there are some changes in the investments in the process. You have to use, for instance, in hot box process, you have to use then these metallic core boxes and so on in steel, not aluminum even. And how can the foundry and the customers earn back this improvement, which we possibly can do to improve the circumstances people are working in the foundry? Because definitely they are not coming to work in lower salaries because they get better environment. No. You have to give that as a surplus, as an additional benefit. And those investments, they are not big investments if we look them as an investment to the future. But the question is, how much is appreciated this step towards better environment? But however, my opinion is that the foundries have to take these steps towards zero emissions and to develop and to be able to survive. And of course, these inorganic binders, they have improved a lot during this project already. And now, when the big binder manufacturers get interested about this, because at the beginning of this project, it was clear that the biggest organic binder manufacturers told to me so that don't even dream that you can use inorganic binders in iron and steel foundries. This is only for aluminum and non-ferrous foundries. But okay, now we see it is possible. But of course, they were protecting their own business, because if they are not in this inorganic binder business, they are going to lose the business. But as a last comment, I would say that I fully agree this comment from foundry industry that when we open the business with countries like India and South America, we have to put as a demand that same rules must be followed. But it's interesting to see how it goes, because we remember when ISO 9000 quality assurance system came up, I saw this personally in India and other Asian countries, that the foundries said that when I was proposing, could Mihanat help you to build up a ISO 9000 system into your foundry? They said that, sorry, Pekka, you are too expensive. We can buy such paper to the wall from administration. And I'm afraid that the same will happen if we put more, so to speak, environmental demands to those countries. There are copying machines to make those, or they can buy from internet. And if the European customers don't check thoroughly, are those reports or those papers, are they copied papers or are they really made papers, then we are in shit. Thank you very much. Kiitos.
Kiitos, Pekka. Thank you, Pekka. So now, are there any other questions from the audience to the representatives and partners? If not, then I thank you all the participants. I calculated in the beginning and during the proposal seminar that we were nearly 100. So it means that this topic is interesting. And as we saw now, so the limit values will be stricter, and somehow we have to know the techniques and the costs, to meet the new legislative and regulations. But I thank you all for presentations and listening our seminar. And as mentioned, we will place all these presentations in our project website. And please contact us or some of our partners if you have any further or new questions. Thank you.
Thank you so much.
Thank you very much.
Thank you.
Thank you. Bye-bye.
Bye-bye.
Bye bye.
Bye.
Bye.